Okay, welcome back to our continuation of the study of energy in electrostatics. Just point of note, I lost my reading glasses, so I had to go steal a pair from my grandmother. That's why I'm wearing granny glasses. So if you're wondering, that's the explanation. So what we're going to do now is we're going to get into a study of the concept of electric potential. Now, what I want you to understand is that there is a difference, and this is important, between electric potential and electric potential energy. The two concepts are related, but they're different things, okay? And it's really confusing, especially when you first encounter this, to hear those two terms, because when we hear potential, we just automatically think potential energy. But as you're going to see, electric potential isn't an energy at all, but it's related to energy. Okay, so that's where we're headed, and I really think the best way to introduce electric potential is just to do a little bit of a quick review over what we've already done with Coulomb's law and the electric field, because there is an analogy between the two steps that go between those two things. Okay, so let's talk about electric potential, and let's start by just doing a quick review. Now, we started out the class by asking ourselves, how do two charged point particles interact with one another? And so here's my picture. I've got a charge over here, big Q, that we typically refer to as the source charge. Maybe this is the charge we set up in the lab. And out here is little q, what we call the test charge. It's the charge that's interacting with this test charge, okay? And Coulomb's law gave us a very basic explanation of how those two charged particles will interact. Coulomb said, hey, if you want to calculate the magnitude of the electric force between those two charged particles, there's a basic equation you can use. And this is the equation that we learned, that the electric force is 1 over 4 pi epsilon naught, or what we sometimes just write as K, times the product of the charges, divided by that distance between them squared, okay? And so that equation right there will give us the magnitude of the electric force. And then we just have to apply what we know about how positive or how charges with the same charge and different charge interact with each other to get the direction. And so we know that if we have two charges that have the same sign, then the force between them is going to be repulsive. If these are both positive or both negative, then they're going to experience forces that are going to push them straight away from each other, right? If the two charges have opposite signs, then the force is attractive. And so what we get is that they'll be pulled together straight towards each other, right? And so that was Coulomb's law, which basically helps us understand how two charged particles, 2 point particles that are charged, will interact with each other. And that'll give us the force. And we know from last semester that if we understand what the force is, then we can use that force to get an acceleration and then apply all those kinematics equations that we learned last semester to predict how an object will move, where it's going to be at a later time, how fast it's going to be moving at a later time, even how fast it will be accelerating at a later time. So knowing forces is really important. But we also said that, hey, we've got some problems with Coulomb's law. It doesn't really take into account time and the need for signals. Say if Q were to shift its position, the big Q, it would take time before little q should know that. But Coulomb's law doesn't imply that. And so how do we get around that? Well, we said, well, let's try to look at this a different way. Instead of trying to consider the two charged particles interacting with one another, let's just consider the one charged particle, big Q, all by itself, and ask ourselves, how does it affect the space that surrounds it? See, Coulomb's law tells us how two charges interact with one another. But we want to know, how does one charge affect the space around it, right? And that led us to introduce this concept of the electric field. So we went to a different picture. We dropped little q out of the picture entirely. And we just began to ask, if I have big Q located right here, what's its effect at this point P that's a distance r away from it? Okay? And we introduced the electric field, and we defined it to have a value that's equal to the magnitude of the electric force at that point divided by the charge that's experiencing that point. In other words, we take this equation right here and we divide out of it this little test charge that's feeling the force from the charge that we're interested in, okay? And so we said, look, the electric field, its magnitude is just the electric force divided by that test charge. And of course, if we apply this to point charges, then what we get is that the magnitude of the electric field is just 1 over 4 pi epsilon naught times the charge that we're interested in, divided by the distance to that point squared. That gives us the magnitude of the electric field. And of course, then we define the direction of the field to be the direction that a positive charge would move if it was placed at that point. And so we could say, hey, if I put a proton here at point P, which way is it going to move because of Q? And we would say, well, if this is positive, it's going to move to the right. And so that would be the direction of our electric field, you know? But see, here's the cool thing about the electric field. It allows us to ask, well, how is this individual point charge acting in space? How's it influencing the space that surrounds it? And it doesn't have any reference to any other charges. So it allows us to look at that one charge by itself and say, you know, what effects is it producing in the area around it? Really, of course, the charge theoretically could influence all of space, right? It's just it gets very small the further away you get. Now, the nice thing is, if we know the electric field value, then that really makes it easy for us to calculate the amount of force that a charge would experience if it was placed at point P, right? So if I take a charge, say a proton, and I put it here, and I want to know, well, okay, I've put it in the electric field of this big charge Q, how much force is it going to experience? Well, this equation tells us how to figure that out. The way we defined the electric field was E equals the electric force over Q. Well, I can do some algebra on this and solve for the electric force, and when I do that, I get that the electric force is just the charge times the electric field. So remember, and this kind of makes sense, the electric field is going to give us units of newtons per coulomb. So if I multiply a newtons per coulomb by something that's in coulombs, the coulombs are going to cancel, and I'm going to get newtons. And so the electric field tells us how a charge by itself affects the space around it. And then if we want to figure out the force that that effect is going to produce on another charge that's placed in that field, then we just multiply that charge by the strength of the field at that point. So it allows us to go from an individual picture to an interaction picture, which is really nice because we want to be able to do that too. Okay, well, here's the thing. The reason I'm bringing all this up, hopefully that's a review. Maybe it reinforced some things that you weren't quite getting, but here's the thing. When it comes to energy, we're going to do the same thing. We're going to take the same approach when it comes to electric potential energy. All right, we're going to move from looking at the potential energy of two interacting charged particles, and we're going to ask, well, what does one particle by itself do to the energetics of space surrounding it? Okay, so let's just go and let's look at our picture. So here we go. We've got, again, our picture of our two charges separated by a distance r, and obviously there's going to be some sort of electrical force between them. Well, we use the nature of that force to derive an expression for the potential energy between those two particles. We found that the potential energy due to the electric force, U sub E, well, it's just this K value, the 1 over 4 pi epsilon naught, times the product of the charges over the distance between them. In other words, notice the difference here. We don't have the squared anymore, it's just R. And that came out of the fact that we integrated that force to get our potential function, right? Of course, this is going to give us units of joules because it's an energy, right? And we also found that, well, if both the charges have the same sign, then the potential energy is going to be positive. And if both the charges, or if the charges have opposite signs, then the potential energy is going to be negative. But we said, look, negative potential energy shouldn't bug us because what we're always concerned with is just changes in potential energy. That's what we use to make predictions about how objects are going to move, right? Okay, so that was the picture we've developed then, basically, of how to calculate the potential energy between 2 point charges. Now, just like before, what we want to do is we want to ask ourselves the question, well, here's the thing. If we could get rid of Q, right, and just focus in on the source charge. Well, we know the source charge produces an electric field everywhere in space around it. Well, maybe it does something to the energetics. I don't know if that's the technical term, that's the word I use, but maybe that charge by itself somehow injects energy properties into the space surrounding it as well that will allow us to determine how much potential energy any other charge put out there would have due to Q, due to the big Q. And so that's what we want to do. We want to know, how does a single charge influence the energetics of the space surrounding it? What does it do out there? And the way we do this is we introduce the concept of what's called electric potential. No energy at the end of that, just potential. Okay? So let's change our picture just like we did before. Now we have our source charge. And this charge up here, it's gone now. Okay? This charge is gone. We just got a point P out here, and what we're saying is, what does Q do? How is its energy effects measured out here at P without respect to this other charge? Okay? Well, the way we do this is we introduce this new concept called the electric potential, and we use the capital letter V to represent that, okay? And the way we define the electric potential is it's just simply the electric potential energy divided by that test charge that's out here interacting with our source charge. Okay? In other words, do you notice the similarities? We went from electric force, divided that by the test charge and got electric field. Now we're going from potential energy, dividing that by the source charge to get potential. So we're taking out of the equation that other little charge that's out there testing the field of our source charge, okay? Now, I want you to notice something before we look at this for the point charge. V is equal to the potential energy over the charge, right? Well, what's that going to do? Units-wise, we're going to get joules over coulombs. So the units of potential are joules per coulomb. Now, I want you to notice something. That is not the energy, or that is not the units of energy. That is something different, okay? It's got energy in it up there in the denominator or numerator in the units, but joules per coulomb is an energy. Joules is energy. So when we're talking about potential, we're not talking about just straight up energy. But instead, we're kind of, as you're going to see, we're talking about what's the potential energy that's there, okay? Now, we'll come back to that. Let's just apply this rule, how we define the potential, to the potential energy of a point charge. Well, if I apply this to a point charge, I'm going to divide this by Q, right, the test charge. That's going to divide this Q right here out. And so what I'm going to get is that the potential energy of a point charge, a distance r away from that point charge, is just going to be 1 over 4 pi epsilon naught times Q over r. Okay? Now, that's what we're doing. But again, what we're looking at is what's the influence of a charge in terms of energy all by itself in the space that surrounds it. Okay? Now, I do want to point out, these units, joules per coulomb, we give those another name. We call those volts. 1 volt, which we represent by the capital letter V, is equal to 1 joule per coulomb. Okay, so now that's probably a term that's a little bit more familiar to you. If you're taking circuits right now, you've probably measured the voltage of things, right? So 1 volt is just equal to 1 joule per coulomb. So when we talk about electric potential, we'll measure it in terms of volts. But don't forget what a volt is. It's a joule per coulomb, okay? We sometimes refer to it as voltage. And you'll hear that. Voltage is used in a lot of different ways. Usually it's used to reference a voltage drop across a circuit element, but or it could be used to measure the amount of electromotive force that's available in a battery or a power supply. But when you're hearing voltage or you hear volts, you're talking about electric potential. Okay? Now here's the cool thing. There is a connection between voltage and potential energy, between the electric potential and the electric potential energy. Go back to the equation. The voltage, or the potential, is equal to the electric potential energy divided by the charge. Well, if I solve this for the potential energy, then what I get is that the potential energy for a charge that's placed at point P here is just equal to the amount of charge that I have at that point multiplied by the electric potential at that point that's due to my source charge. In other words, I just take the charge times my potential. Okay? So for example, say this was 2 joules per coulomb, 2 volts right here. Okay, that was the potential. Well, if I place 1 coulomb there, well, think about what 2 volts is. It's 2 joules per coulomb. What that means is for every coulomb I put there, I get 2 joules of potential energy. So if I put a coulomb of charge here, I'm going to get 2 joules of potential energy. I'm just multiplying them. If I put 4 coulombs here, then I'm going to get, let's see, if I have 2 volts, 2 joules per coulomb, I put 4 coulombs there. All right, I get 2 joules for every coulomb. I've got 4 coulombs. That's going to be 8 joules of potential energy. So the key is, if we know the potential at any point in space, then we can quickly find the potential energy of any point charge that's placed at that point. And that's useful to know because in the lab, it's real, or when you're dealing with circuits, you usually don't, you're never going to measure the electric field. You won't be able to figure that out. What you'll measure is the voltage. You'll measure the voltage drop across elements and stuff like that. And you'll be able to use that to figure out how much energy, say, is dissipated in a resistor or how much energy stored in a capacitor. And so the voltage in a circuit, that's very important. So this concept of electric potential, it's what we tend to speak of when we're working with circuits. Okay, now we're going to get into some examples in the next video of how to use this for point charges. But what I want to do first is I want to think still a little bit qualitatively about how's the voltage useful in helping us make predictions about the behavior of the motion of charged objects. Because remember, in physics, that's what we're all about. We want to be able to predict. We want to know what to expect as particles move, as objects are moving. You know, what can we predict down the road about their behavior? And so the voltage concept, the potential concept, is very useful in those terms. I want to go over something that your book goes over, but I think your book does it a little abstractly, and I want to put hard numbers on stuff to help us think about it. You see, here's the thing. If we know how the potential changes in some region of space, then we can predict how charges are going to move in that region. Let's just consider an example. Let's say that we have 2 points, and we know that the potential at this point down here is 5 volts, and the potential at this point is 10 volts. Now, you can see that going from here to here is, this is going through a path of increasing voltage, my increasing potential. I really wish I'd used the word potential there. If I say voltage, that also means potential. Just get used to that, okay? So this is increasing potential as we go from the 5 volts to the 10 volts. Well, now let's think about this for a moment. Let's say that I put a 2 coulomb charge down here at this point. I've offset it so we can still see the point, but this guy is like right on top of this in the way I really want you to see it. So we've got a 2 coulomb charge down here at this 10 volt point. Well, what would its potential energy be? Well, the potential energy is just the charge times the potential. And so if I substitute my 2 quantities in there, I'm going to get 20 joules. 2 coulombs times 10 volts gives me 20 joules of potential energy. So that would be the potential energy here. Now, what if instead I had placed this 2 coulomb charge down here? Well, 2 coulombs times 5 volts would give me 10 joules of potential energy. And so what we find is that for this positive charge, as we go from our 5 volts to our 10 volt position, we're actually increasing our potential energy. Now, think about what that's going to mean. Okay? Remember, the electric force, which is what all this stuff's going back to, all this is due to an electric force. Okay? The electric force is conservative. So mechanical energy is conserved. And so that means that my potential plus my kinetic always has to be the same value. So if I'm increasing my kinetic or my potential energy, that means that my kinetic energy has to be going down, right? Well, if my kinetic energy is dropping, what's that mean about the speed at which this charged particle would be moving, say, if it goes from here to here? Well, if it's moving from here to here, it's increasing its potential energy, it's decreasing its kinetic energy. Well, if the kinetic's going down, it's going to be moving slower, right? So here's what we find. If my change in potential is greater than 0, which is just a way of saying I'm going from a low potential to a high potential, then a positive charge is going to slow down, right? Because the kinetic's got to go down, right? And so it shouldn't be surprising if my positive charge was moving from the 10 volts to the 5 volts, well, I'm losing potential energy going between these 2 points. If I'm losing potential energy, then I'm gaining kinetic energy, so my speed is going to increase. So whenever we have a change of potential that's less than 0, which is just a way of saying I'm moving from a high potential to a low potential, then what we're going to get is that a positive charge will speed up. And so that helps us make predictions. If we shoot a charged particle into a region and it's positively charged and it's going from a low potential to a high potential, we expect it to slow down. Okay? And vice versa, if we inject it into a region where it's going from a high potential to a low potential. Okay? Now, I want to show this. Your book doesn't talk about it, but I think it's worth considering. Say we have the same scenario we started up with here, but now we have a -2 Coulomb charge. So now let's ask ourselves, what's going to happen if it was a negative charge? Because we have to realize that when we're dealing with charge, we got positive and negative, and they tend to behave a little differently, right? Okay, well, let's take a look at this. Then if I have a -2 Coulomb charge I put here, well, what's my potential energy going to be? Well, again, it's Q times V. Put that in. Now I get -20 joules. The negative comes from the fact that it's a negative charge. But again, don't remember, it's not what the value of the potential is at any point that really matters. It's how it changes from one point to another. Okay? So don't let the negatives throw you off. All right. So if I put my -2 coulombs here, it's going to be -20 joules. Well, if I put it down here, you can see fairly quickly, I'm going to get -10 joules at that point. So let's think about what's happening. As we move from this point to this point, we're going from -10 to -20. That's a decrease because -20 is less than -10. All right? So if I have my negative charge moving from here to this place, in other words, it's going from the low voltage to the high voltage, right? From low potential to high potential, it's losing potential energy. And if it's losing potential energy, it's got to be picking up kinetic, and so it's going to speed up. And so what we find is that when we're moving from a low potential to a high potential, and it's the negative charge that's going to do it, then you're going to speed up in that case. Again, that's a predictive power. We know what to expect. And then, of course, vice versa. If my negative charge is going from here over to here, then as it does that, it's going from a low potential energy to a higher potential energy. It's picking up potential energy, right? Well, if it's picking up potential energy, it's got to lose kinetic energy. That means it's got to slow down. So for a negative charge, if we're moving from high potential to low potential, that negative charge is going to slow down. Here's the key to remembering this. If you can get the positive charge down for how it's going to work, the negative charge just does the opposite. But again, conceptually, what I'm wanting you to think about is that this gives us the ability to kind of predict. We learn what to expect for the behavior of an object that's moving through 2 different realms or 2 different potentials values, okay? So this is kind of the introduction. What I'm going to do in the next video is work out a couple examples to show you how we deal with potential for point particles. And then after that, we're going to move into parallel plates, because that really sets the stage for parallel plate capacitors. Okay, so good luck with this. If you have any questions, let me know.